There are real numbers whose first 10,000 digits, if a human ever knew them, would settle every unsolved problem in mathematics. The Riemann Hypothesis, the Goldbach Conjecture, P versus NP. Every question mathematicians have ever asked, encoded inside a string of digits about the length of a short essay. The catch is that no computer can ever calculate them. Not in principle, not with a faster machine, not ever. That is one number out of 12 we will meet in this video. 12 famous real numbers, in order from the strangest to the most familiar, each with a single fact so surprising that mathematicians spent decades, sometimes centuries, refusing to believe it. Some are constants you have known since high school. Others are obscure enough that most professional mathematicians could not tell you their first 3 digits. Almost all of them have at least one open question attached that no human alive will solve. By the end of this video, you will understand why the real number line is the strangest mathematical object ever discovered, why famous does not mean understood, and why the gap between knowing a number's name and knowing what that number actually is can be wider than the gap between any two integers. We start with the strangest. There is a real number called omega. It is the probability that a randomly chosen computer program will eventually halt. It was defined by Gregory Chaitin in 1975. Omega is uncomputable. That is not a statement about practical difficulty. It is a theorem. There is no algorithm, no shortcut, no clever trick that can produce the digits of omega one after another. Most real numbers, in fact, cannot be computed at all. But omega is special in a way no other uncomputable number is. If you knew the first n bits of omega, you could decide for every computer program shorter than n bits, whether that program halts. From the halting problem, you could resolve the truth of any mathematical statement that can be expressed as a halting question, which is almost every open problem in number theory. The Riemann Hypothesis, the Goldbach Conjecture, the twin prime conjecture, the existence of odd perfect numbers. Knowing roughly 10,000 bits of omega would in principle give you the answers. We have computed 12 bits of omega for one particular universal machine by Khalud and Deneen in 2002. Bit 13 is open. Omega is a real number. It sits on the number line between 0 and 1 at a specific location. It just happens to be a location no computer can ever point to. In 1844, Joseph Liouville set out to do something nobody had done: to construct, on demand, a number that no polynomial with integer coefficients could ever have as a root, a transcendental number, written down explicitly. Liouville's constant was the answer. Its decimal expansion is 0.110001, followed by a desert of 17 zeros, then a 1, then 95 zeros, then a 1. The ones sit at decimal positions equal to 1 factorial, 2 factorial, 3 factorial, and so on. Everywhere else is 0. Liouville proved this number is transcendental by showing that any algebraic number cannot be approximated by rationals as well as his constant can. The rapidly increasing gaps of zeros make it approximable to a degree no algebraic number can match. This was 30 years before Hermite proved that E is transcendental, and 38 years before Lindemann did the same for pi. Liouville did not wait for the famous constants to be classified. He simply built a transcendental from scratch and proved its credentials. The number itself has no application. It does not appear in physics, but it stands as the first concrete proof that transcendentals are constructible, and that, in fact, almost every real number is 1. David Champernowne was a Cambridge undergraduate in 1933 when he wrote down the following number: 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, the digits of every positive integer, concatenated forever. He then proved that this number is normal in base 10. A normal number is one in which every digit appears with frequency exactly 1/10. Every 2-digit block, and there are 100 of them, appears with frequency exactly 1/100th. Every n-digit block appears as often as it should on average forever. Normal numbers are, in a precise sense, the most statistically random real numbers possible. Émile Borel proved in 1909 that almost every real number is normal. But here is the catch. Out of all the famous constants in mathematics, pi, e, the square root of 2, the golden ratio, the Euler-Mascheroni constant, not a single one has ever been proven normal in any base. We can write down a normal number on demand. We cannot prove that the most studied irrationals in mathematics are normal. Champernowne's constant exists to make that gap painfully visible. The harmonic series, 1 plus 1/2 plus 1/3 plus 1/4, and so on forever, diverges. It grows, roughly, like the natural log of n, but it grows slightly faster than the log, and the difference between them, in the limit, is a specific real number. It is called the Euler-Mascheroni constant, written as gamma. Its value is 0.577-21566. Leonhard Euler discovered it in 1734. Gamma shows up everywhere. In number theory, in probability, in the asymptotic behavior of countless famous functions. It is one of the most ubiquitous constants in all of mathematics. And nobody knows whether it is rational. 290 years after Euler computed its first 16 digits, the question of whether gamma is a ratio of two integers, or whether it is irrational like pi, or whether it is transcendental, that question is completely open. We have computed gamma to hundreds of billions of decimal places. We do not know what kind of number it is. If gamma turns out to be rational, the denominator of its lowest terms fraction must be larger than 10 to the 242,080. That is a constraint. It is not a proof. This is one of the most famous open problems about a specific real number in all of mathematics. Almost nobody outside the field has heard of it. Take any real number. Write it as a continued fraction, a sequence of positive integers obtained by repeatedly stripping the integer part and inverting. The continued fraction of pi begins 3, 7, 15, 1, 292, 1, 1, 1, 2, 1, 3. Compute the geometric mean of those integers going further and further out. Alexander Khinchin proved, in 1934, that for almost every real number, this geometric mean converges to the same specific constant, approximately 2.6854. The choice of number does not matter. Pi, e, the square root of 17, a randomly chosen real, the continued fraction geometric mean is almost always the same. Khinchin's constant k0, but there is a catch. For pi, e gamma, the square root of 2, the golden ratio, every famous irrational we know, we have no proof that the limit even exists, let alone equals k0. Numerically, the partial geometric means for pi and e wander toward k0. They look like they are converging. We just cannot prove it. The almost every in Khinchin's theorem excludes a set of measures 0. The famous irrationals might lie in that exceptional set, or might not. Nobody can tell. In 1975, Mitchell Feigenbaum was working at Los Alamos when he noticed something he could not explain. Take any simple dynamical system that doubles its period as you turn a parameter. The logistic map, the Khinchin map, dripping faucets, certain electrical circuits, certain population models. As the parameter turns, the period doubles again, at smaller and smaller increments. The ratio of successive increments approaches a specific constant. That constant is approximately 4.669201, and it is the same constant for every system. Feigenbaum delta does not depend on what equation you start with. The logistic map and a dripping faucet, two systems with no physical relationship, produce the same ratio. It is a universal constant of period doubling cascades, the way pi is the universal constant of circles. Feigenbaum's discovery is one of the strangest results in 20th century mathematics. It says that the route to chaos is the same in every smooth one-parameter family, with a quadratic maximum, regardless of what physical system you describe. We have measured Feigenbaum delta in turbulent fluid experiments. The value matches the theoretical prediction to many decimal places. We do not know whether Feigenbaum delta is rational or irrational. Nobody has proved either way. Write down the number 1. Now describe what you just wrote out loud. 1, 1. Write that down. Now describe that. 2 1s. Write down 21. Describe it. 1211. Write down 1211. Repeat forever. The sequence grows 1, 11, 21, 1211, 312211, and so on. As you keep going, the length of each term grows by a constant multiplicative factor. That factor approaches a specific real number. John Conway studied this sequence in 1986 and proved that the constant is approximately 1.303577. He then proved something stranger. The look-and-say constant is algebraic. It is a root of a polynomial with integer coefficients, and the polynomial has degree exactly 71. The look-and-say sequence is a child's game. The asymptotic growth rate of a child's game is the largest real root of a specific polynomial of degree 71. That polynomial has been written down. Its coefficients are known. Mathematics keeps finding order, and the order keeps being more specific than anyone expected. The golden ratio is the number you get when you cut a line segment so that the whole length divided by the longer part equals the longer part divided by the shorter part. Euclid wrote it down 23 centuries ago and called it the extreme and mean ratio. Its value is 1.618034. Its continued fraction is the simplest possible, 1, 1, 1, 1, 1 forever. That simplicity is the source of a deep theorem. The golden ratio is, in a precise mathematical sense, the most irrational number that exists. No other irrational is harder to approximate by rationals. Adolf Hurwitz proved this in 1891. The golden ratio also appears as the limit of ratios of consecutive Fibonacci numbers. It governs the geometry of the regular pentagon and the regular icosahedron, and shows up in the spiral arrangement of sunflower seeds and pinecone scales. But its most precise mathematical meaning is the one most people never hear. It is the irrational number that resists rational approximation the most. Among the worst approximable numbers, the golden ratio sits at the very top. Take the function whose derivative equals itself. There is essentially only one such function. It is the exponential function with base e. The constant e is approximately 2.71828. Jacob Bernoulli encountered this number in 1683 while studying compound interest at progressively shorter intervals. Euler named it, proved it irrational in 1737, and used it as the natural base of the logarithm. Charles Hermite proved that e is transcendental in 1873, a result that 8 years later gave Lindemann the tools he needed to prove the transcendence of pi. The number e shows up in nearly every continuous process in nature: radioactive decay, cooling, charge across a capacitor, compound growth, the intensity of light through an absorbing medium. The reason for the ubiquity is that e is the only base for which the exponential function is its own derivative, and most natural processes are governed by differential equations, in which the rate of change is proportional to the current state. That makes e the natural language of continuous change. Without e, calculus would still work. With e, the formulas are clean. That is the test of a fundamental constant. In 1545, Girolamo Cardano was solving cubic equations and ran into something impossible: a square root of a negative number appearing as an intermediate step in his formula. He called it subtle and useless, but kept it in the calculation. The final answer came out real. The square root of -1, written as I, turned out to be the missing ingredient that completes the algebra of polynomials. Every polynomial of degree n has exactly n roots, no exceptions, if you allow I. For more than 200 years after Cardano, mathematicians used I with suspicion. Raphael Bombelli formalized its arithmetic in 1572. Euler standardized the symbol in 1777. The breakthrough came in 1831, when Carl Friedrich Gauss showed that I has a geometric meaning. The real numbers live on a line. The complex numbers, combinations of a real part and an imaginary part, live on a plane. Multiplying by I is a 90-degree rotation. That single observation turned I from a strange algebraic ghost into a tool for describing rotation, oscillation, and wave propagation. Modern physics could not be written without it. It took 286 years to go from Cardano's subtle and useless to electromagnetism. Mathematics moves slowly. The ratio of a circle's circumference to its diameter is approximately 3.14159. Archimedes computed it using nested polygons to 2 decimal places around 250 BC. For 2,000 years after Archimedes, pi was just a number that mathematicians computed to more and more digits. Then in 1882, Ferdinand von Lindemann proved that pi is transcendental. That single theorem killed an entire field of ancient mathematics, the problem of squaring the circle. For more than 2,000 years, mathematicians had tried to construct a square with the same area as a given circle, using only a compass and straight edge. Lindemann proved that no such construction can exist. Any number constructible with compass and straight edge is algebraic. Pi is not algebraic. Therefore, there is no square. Pi was the first famous constant whose nature was completely settled. We still do not know whether pi is normal in any base. We do not know the precise relationship between pi and e, whether pi plus e is irrational, whether pi times e is irrational. We do not know nearly as much about pi as we think, but its transcendence ended a problem that had occupied humanity for 20 centuries. We close where everything began, with a number that nobody invented and nobody named. The square root of 2. The length of the diagonal of a unit square. Approximately 1.414213. The Pythagoreans believed, as a philosophical principle, that every length could be expressed as a ratio of integers, that the universe was made of ratios, whole numbers and their fractions. The square root of 2 destroyed that belief. It is not a ratio. It cannot be expressed as 1. The proof is short. Suppose it were a ratio in lowest terms, square both sides, count factors of 2, and it contradicts itself in 3 lines. Legend says that the Pythagorean who proved this, Hippasus of Metapontum, was thrown into the sea by his own brotherhood for revealing the contradiction. The legend may not be true, the mathematics is. The discovery of the square root of 2 was the first time mathematics produced a result that destroyed its own foundations. It started a crisis that took 2,000 years to resolve, ending only with the rigorous construction of the real numbers in the 19th century. Every number we have met in this video, omega, Liouville, Champernowne, gamma, Khinchin, Feigenbaum, Conway, phi, ei, pi, is in some sense a descendant of the square root of 2, the first crack in the rational picture. 12 numbers. 1 is uncomputable. 2 are open problems older than the United States. 2 are universal across every system that contains them. 3 are constants every high school student knows. 1 is purely imaginary. 1 destroyed a philosophical movement. Together they are a thin slice of the real number line, a line that contains uncountably many transcendentals, an uncountable set of uncomputable reals, and infinitely many normal numbers we cannot identify. The next time you see a number on a page, ask what kind of number it is. Rational, algebraic, transcendental, normal, computable, named. Most of the time the answers are unknown. That is the strange truth about the most basic object in mathematics. We have written down a tiny portion of the number line. The rest is dark,